So I want you to imagine uh, trying to run a marathon.
Okay.
Like, you've put in the hours, your cardiovascular system is just totally primed, and, your muscles are conditioned to fire with absolute precision.
But you're at peak performance.
Exactly. You basically have the raw power to run a sub-2-hour race. But there is this massive, unavoidable physical constraint imposed on you right at the starting line.
I feel like a catch is coming here.
Oh, there is. You have to run this entire race wearing a thick, heavy mountaineering parka.
Oh, wow. Yeah, that sounds miserable.
Right. And it wouldn't matter how optimized your stride is or like how efficiently your lungs process oxygen. Within the first few miles, your core temperature would just absolutely spike.
Because the heat has nowhere to go.
Exactly. Your biology, acting purely on self-preservation, would forcefully intervene. Like, you would be compelled to slow down, not because you lack the muscular strength, but simply because you cannot shed the heat you are generating.
Yeah, your speed in that scenario is entirely dictated by your thermal limit.
And it's this brutal biological reality, but it perfectly mirrors the physical crisis that's currently playing out at the absolute bleeding edge of technology.
It really does. It's the exact same problem.
Right, because we are building these incredibly powerful computational engines, like these massive arrays of silicon that possess almost incomprehensible processing power.
But we are deploying them in environments where they simply cannot shed their thermal energy fast enough.
Yes. The heat isn't just some annoying byproduct anymore. It is literally the ceiling.
And that's fascinating because when we think about artificial intelligence, we rarely think about ceilings.
No, not at all. We think about algorithms, neural networks, and, this weightless concept of the cloud.
Right. The cloud sounds so ethereal and floaty.
Exactly. But you look at the physical infrastructure powering AI, and it is violently physical.
Yeah, it requires dense, incredibly heavy, incredibly power-hungry machinery.
And that brings us to what we're doing today in this deep dive. We are looking at a really detailed white paper co-authored by Supermicro and NVIDIA.
Yeah, it's titled Comparison of Air-Cooled versus Liquid-Cooled NVIDIA GPU Systems.
And what I love about this source is that it completely strips away all the ethereal, marketing fluff of AI and forces you to look straight at the plumbing.
The literal plumbing in this case.
Right. Because how a computer sweats, like how it physically removes thermal energy from its processors, is now the single most critical variable dictating AI performance.
And not just performance, but multi-million-dollar operational budgets. And honestly, the viability of our entire power grids.
So our mission today is to figure out exactly why cooling is no longer just this background facility issue, but the main event.
Yeah, because for the longest time, thermal management in data centers was just relegated to facility engineering.
Right, like the IT guys didn't worry about it.
Exactly. You just stacked the servers in a massive room and you pumped that room full of freezing air. It was essentially industrial brute force.
Just crank the AC and hope for the best.
Pretty much. But this Supermicro and NVIDIA paper demonstrates that the brute force era is officially over.
Because the hardware required to train foundation models, like these massive GPU clusters, they generate a heat density that ambient air simply cannot handle anymore.
Right, we are packing thousands of chips into incredibly tight physical footprints.
Which means we are essentially putting that marathon runner we talked about in a thicker and thicker coat.
A very expensive coat.
Yeah, no kidding. So to figure out exactly how much that coat is restricting performance, this white paper sets up a head-to-head hardware shootout.
And I really want to look at how they structured this, because they didn't just run some, abstract software simulation.
Right. They didn't just do the math on a whiteboard.
No, they built two massive physical systems side by side.
Okay, so let's break down the battlefield here. What exactly did they build?
We are talking about two identical arrays,
Mhm.
and each one is packing 8 NVIDIA H100 80-gigabyte GPUs.
And just for context, the H100 is essentially the engine block of the modern AI boom, right?
It is the gold standard chip right now. So one of these systems is cooled by traditional air methods.
So heat sinks and high-speed fans.
Exactly. And the other utilizes direct-to-chip liquid cooling.
Okay, but I read the source pretty closely, and I have a question about this setup.
Sure. What is it?
So the methodology looks rigorous, but there's this subtle nuance in the host systems running those GPUs.
Oh, you mean the CPUs?
Yeah. They disclose that the liquid-cooled system was built using dual AMD EPYC 9474X processors, and those are 48-core CPUs.
Right.
But then the air-cooled system used dual AMD EPYC 95334 processors, which have 64 cores.
Good catch.
Well, wait, if the CPUs are literally different, doesn't that inherently introduce a massive variable?
Me, you would think so, right?
Yeah, like how can they claim this is a definitive head-to-head test if the host processors driving the whole thing have a completely different core count? Doesn't that invalidate the comparison?
It absolutely would if we were testing general-purpose CPU compute.
Okay, but we aren't.
Exactly.
Hmm,
In the architecture of a modern AI training node, the CPU plays a highly specific but mostly peripheral role.
like a manager.
Kind of, yeah. The CPU manages the operating system, it handles the storage inputs and outputs, and it basically orchestrates the PCIe lanes to feed data into the GPUs.
So it's just shoveling coal into the furnace.
That is a great way to put it. The actual heavy lifting, the dense matrix multiplication required for large language models, that happens entirely on those 8 H100 GPUs.
So the CPU core count doesn't really matter as long as the data keeps flowing.
Right. By thoroughly documenting that CPU variants, Supermicro, and NVIDIA are actually just being mathematically transparent.
Ah, okay.
They are proving that as long as the GPUs are constantly fed with data, that slight difference in host CPU core count has a statistically negligible impact on the massive thermal and power draw metrics of the GPUs themselves.
So the focus stays completely locked on the identical GPU arrays.
Yes, the furnace is what we're measuring, not the guy shoveling the coal.
Okay, that makes total sense. So let's look at the actual mechanics of these two cooling systems before we get into the crazy temperature readings.
Yeah, because air cooling sounds really simple, but at this industrial scale, it's a massive mechanical effort.
So how does the air cooling actually work in these servers?
Well, traditional air cooling relies on the principle of convective heat transfer using ambient air,
So just blowing room temperature air over hot metal.
basically. Inside these servers, you have a series of embedded cooling fans. And these aren't like the little quiet fan on your laptop.
Right, I've been in a data center. They sound like jet engines.
Exactly. These are deep, high RPM industrial rotors that pull cold air from the front aisle of the data center, drag it violently across metallic heat sinks attached to the hot silicon, and then exhaust the heated air out the back.
It's the legacy standard. We've been doing it this way for decades.
We have. But from a purely physics perspective, air is a terrible thermal conductor.
Wait, really?
Yeah, its specific heat capacity is incredibly low.
Oh, right. That's why double pane windows have a layer of air between them.
Yes.
We literally use air to stop heat from...
Exactly. Air is an insulator. So to compensate for air's poor thermal conductivity in a server, you have to move an absolutely massive volume of it very quickly over a very large metallic surface area.
So you just have to use sheer force.
Right. Now, direct-to-chip liquid cooling bypasses that entirely.
Because liquid is better at moving heat.
Way better. Liquid coolants, like specialized engineered fluids or even treated water, have a thermal conductivity that is orders of magnitude higher than air.
But how does it actually interact with the chip, though? Like, we aren't just dunking the motherboard in a fish tank here.
Right. Oh, no. This is highly precision engineered closed-loop cooling.
Okay, walk me through that.
So a highly conductive cold plate is mounted directly onto the silicon die of the H100.
Right, on the chip itself.
Yes. And inside that cold plate are microscopic channels, which they often call skeeved fins.
Skeeved fins, got it.
So cold liquid is pumped through these microchannels under pressure. And because the liquid has such a high thermal mass, it absorbs the heat directly at the point of generation.
Like, literally millimeters from the transistors that are doing the math.
Exactly. Then it flows out of the server chassis to a centralized heat exchanger.
So you completely eliminate the massive metallic heat sinks.
Right. And more importantly, you eliminate the reliance on air as a middleman.
Wow. Okay, so if water is that much better at conducting heat, I want to know what that actually looks like on the physical silicon during this test.
The numbers are pretty stark.
Yeah, like, are we talking about a couple of degrees of difference, or is it a completely different thermal environment?
It's a completely different environment. Under identical workloads, the direct-to-chip liquid cooling system kept the GPUs operating between 46 and 54 degrees Celsius.
Okay, 46 to 54.
But the air-cooled system, meanwhile, ran between 55 and 71 degrees Celsius.
71 degrees. Wow.
You really have to look at the top end of that delta. 71 degrees versus 54 degrees.
That's a 17-degree difference.
And in the world of semiconductor physics, a 17-degree Celsius difference isn't just like a comfort metric.
What do you mean?
It fundamentally alters the electrical properties of the chip itself.
I want to push on that for a second. Let's say you're a facility manager, right? And you're staring at a dashboard.
Okay.
The air-cooled chips are reading 71 degrees. Now, that's hot to the touch, sure. But A modern GPU is rated to survive temperatures well into the 80s or 90s before it hits a critical thermal shutdown, right?
Right, it won't just turn off at 71.
Exactly. So if the server isn't catching fire and the chip isn't actually melting, why should you care if it's 50 degrees or 70 degrees? A functioning chip is just a functioning chip.
See, that assumption right there
Hmm.
is the core reason this white paper is so incredibly important.
Oh, really?
Yes, because a functioning chip is absolutely not a static entity. It changes based on its environment.
Okay, how so?
To understand why 71 degrees is a massive penalty, we have to talk about how modern microprocessors regulate their own survival.
Okay.
There's a mechanism called dynamic voltage and frequency scaling, or DVFS.
DVFS, let's break that down. What is the chip actively doing with this?
So think of an H100 GPU as a highly intelligent, self-regulating organism.
Okay, I like that.
It is constantly monitoring its internal telemetry. It's checking its workload, its power draw, and critically, its temperature across multiple microscopic zones on the die.
So it knows exactly how hot it is at all times?
Yes, and DVFS is the system it uses to balance its performance
Right.
with the laws of physics.
How does it balance it?
It dynamically adjusts its voltage, which is the electrical pressure driving the transistors,
Right.
and it also adjusts its frequency, which is the clock speed, or basically how many billions of calculations it executes per second.
And obviously, it wants to run as fast as possible, right?
Exactly. It always wants to operate at its absolute maximum frequency.
So what stops it?
Silicon have a physical limitation. As the chip gets hotter, electrical resistance naturally increases.
Just from the heat.
Yes, this is a fundamental property of the material.
Yeah.
And increased resistance causes what's called leakage current.
Leakage current. Okay, that sounds bad.
It is. To overcome that resistance and maintain stability at those high speeds, the chip realizes it needs to pull more voltage.
So it pulls more power?
Right. But pulling more voltage exponentially increases the heat being generated.
Oh, I see. It is a vicious compounding cycle.
Exactly. It's a death spiral.
So if the air-cooled chip is sitting there at 71 degrees, it's dangerously close to that compounding cycle.
Yes, it is right on the edge.
So it has to ride the brakes.
Precisely. The chip's telemetry realizes it has very little thermal headroom.
Thermal headroom.
Yeah, if it allows the frequency to stay maxed out, the temperature will just spiral out of control and permanently damage the physical architecture of the chip.
So the chip has to choose between speed and survival.
Right. So the DVFS mechanism forcefully steps down the clock speed. It throttles itself.
It is artificially bottlenecking its own computational capability purely to survive the hostile thermal environment of the air-cooled server.
That is exactly what is happening.
But the liquid-cooled GPU, the one chilling at 54 degrees, it's looking at a completely different internal reality.
Exactly. The liquid-cooled chip sees an abundance of thermal headroom.
Because the liquid is just carrying the heat away instantly.
Right, the heat is being wicked away so aggressively by those microchannels that the chip can sustain its maximum optimal voltage and frequency indefinitely.
Wow, so the DVFS algorithm never has to hit the brakes.
It never hits the brakes. It just runs wide open.
And the data in the paper on the payoff for taking the brakes off is just incredible.
It really is.
Like, by maintaining that thermal headroom, the liquid-cooled system achieved a 17% higher computational throughput during synthetic stress tests.
Yeah, and 17% is a massive number in infrastructure engineering.
I mean, you are extracting nearly a fifth more raw computational power from the exact same physical silicon.
Exactly. If an organization is deploying a fleet of, say, tens of thousands of GPUs, and each one costs tens of thousands of dollars, a 17% throughput increase completely transforms the entire return on investment profile of the data center.
You're basically getting thousands of free GPUs worth of performance just by cooling them better.
Exactly.
But the paper doesn't just rely on those synthetic stress tests, though. They've validated this on actual real-world AI architecture.
Right. They wanted to see how it performs on the stuff people actually care about right now.
Right. So they ran large language models and complex vision language models, and the liquid-cooled system delivered 1.4% faster training times on these massive, sustained workloads.
Now, a 1.4% speed increase might sound a little trivial at first glance.
Yeah, compared to 17%, 1.4% seems kind of small.
But you have to think about the scale. If you're trading a foundation model that requires 3 straight months of nonstop compute time across thousands of chips.
Oh, right. Shaving 1.4% off a multi-month run is actually a massive logistical win.
It frees up millions of dollars in compute capacity for the next task.
It absolutely does. The hardware is physically faster because it's physically cooler.
Right. The thermal barrier is removed, allowing the silicon to operate at its theoretical maximum.
But the speed increase, while totally vital, is arguably only the secondary finding of this research.
Oh, for sure.
Right, because if we transition from looking at computational speed to looking at electricity, the economics of this whole thing changed completely.
The true revelation here isn't just about the physics of heat, it's about the physics of power draw.
Right. We are talking about power numbers that dictate whether an AI project can even secure grid approval to be built in the first place?
Yeah, when we talk about training clusters of this magnitude, electricity isn't just a line item on an operational expense sheet.
It's the whole ballgame.
It is often the hardest physical constraint to solve. Securing a 50 megawatt or 100 megawatt power agreement from a local utility takes years.
So efficiency is mandatory.
Absolutely mandatory.
And the white paper lays out a very clear baseline for this. During active production workloads, they measured the total power draw of both systems.
Right.
And the direct-to-chip liquid-cooled nodes drew an average of 5.2 kilowatts,
Okay.
while the air-cooled nodes drew an average of 6.2 kilowatts,
That is a consistent, flat 1 kilowatt reduction per node.
which represents a 16% reduction in node-level power consumption.
But if I'm reading a study like this, my immediate skeptical reaction is, well, how do we know the liquid-cooled system wasn't just processing slightly less data?
Oh, like maybe it used less power because it was quietly slacking off during the test run?
Exactly. How do we know they're actually doing the exact same amount of work?
It is the very first question any data scientist would ask.
Right.
And the researchers at Supermicro and NVIDIA proactively answered it using rigorous statistical validation.
They couldn't just assume the workloads were identical.
No, they had to prove it mathematically. So they utilized a paired t-test on the GPU utilization metrics during the large language model training runs.
Okay, let's unpack the mechanics of that. What exactly does GPU utilization measure at this level?
So GPU utilization measures the percentage of time that the streaming multiprocessors, which are the core calculation engines inside the GPU, are actively executing instructions versus just sitting idle waiting for data.
Oh.
And in these LLM runs, they pushed the systems to near absolute saturation.
Like running them as hard as they could.
Yeah. The utilization for both systems was sustained between 93% and 95%.
They were essentially redlining the engines for the entire test.
Exactly. And the paired t-test is a statistical tool designed to determine if the mean difference between two sets of observations is actually significant.
So what did the t-test reveal?
When they ran it on the utilization data, the mean difference between the liquid and air systems was a microscopic plus or minus 0.04%.
0.04%. Wow.
Right. Furthermore, the power draw variation, like the actual physical pulsing of electricity as the calculations occurred, showed an identical standard deviation of 170 watts across both systems.
So by isolating those variables, that tiny 0.04% difference proves the chips are doing the exact same mathematical heavy lifting.
The silicon brains are expending the exact same effort.
Which means that entire 1 kilowatt gap in power consumption has absolutely nothing to do with computing.
Nothing at all. The core computational baseline is identical.
So the entire 1 kilowatt delta is literally just the localized cost of thermal management.
Yes, it's the cost of the coat.
Exactly.
But the paper reveals that this 1 kilowatt number isn't even static. It fluctuates based on a phenomenon they call the scaling effect.
Oh, this part is fascinating.
Yeah, the power savings widen dramatically depending on how aggressively you push the AI.
This is a crucial behavioral characteristic of air cooling. Its inefficiency isn't linear at all.
It compounds under stress.
Right. So how did they test this scaling effect?
They tested it across different workload intensities. For lower intensity workloads like running EVL or XCL-IP models, the GPU utilization sat around 60%.
So the chips were basically just jogging.
Yeah.
Yeah.
At this level, the power savings from liquid cooling are present, but they're relatively modest. You see reductions of anywhere from 100 to 400 watts per node.
Okay, that's not huge.
Right. There's even a specific line in the data for the XCL-IP model where the difference was merely 85 watts.
Because at 60% utilization, the silicon just isn't generating a critical density of heat yet.
Right. The ambient air moving at a moderate pace is sufficient to keep the temperature relatively stable.
But modern foundation models are not designed to jog.
No, They are designed to sprint continuously.
So what happens when they sprint?
When they feed it to high-intensity workloads, like fine-tuning LLMs or running dense vision architectures like Vita C-Leap, the utilization spiked to that 95% mark.
And this is where the scaling effect kicks in violently.
Violently is the right word. The power savings jumped to an average of 1.2 kilowatts per node.
Wow.
And during the absolute peak demands of the Vita CLP workload, the liquid-cooled system saved an astonishing 1.5 kilowatts per node.
The gap expands so drastically because of the mechanical desperation of an air-cooled system trying to survive extreme thermal loads.
Right. I kind of picture it like a heavy truck driving up a mountain.
Okay, I like that analogy.
If you are cruising on a flat highway at 60%, the engine is warm, but the natural airflow through the grill keeps it fine.
Right, no stress.
But when you hit a 15% grade and you absolutely floor the accelerator, the engine starts generating a massive concentrated amount of heat.
Right.
And if you rely entirely on air cooling, the truck's radiator fans have to spin up to an agonizing speed just to stop the engine from seizing.
Right, they have to work overtime.
But spinning massive industrial fans requires an enormous amount of electricity from the alternator, which creates a parasitic drain on the very engine you are trying to push up the hill.
So the harder you work, the more power you waste, just trying to breathe.
Exactly. That analogy maps perfectly to the physics of server airflow.
It does. And the white paper actually dissects that 1.5 kilowatt maximum difference to show exactly where all that wasted power is going.
Because 1,500 watts is a lot of power to lose.
It is. So first, they looked at the GPUs themselves. Because the liquid-cooled GPUs have that thermal headroom we discussed earlier, they suffer less from electrical resistance and leakage current.
Right, the DVFS isn't fighting them.
Exactly. That raw electrical efficiency actually saves about 20 watts per individual chip.
Okay, let's do the math on that. 20 watts per chip. There are 8 chips in the node, so that accounts for roughly 150 watts of the savings.
Right.
But that leaves an absolutely massive gap.
It does.
If the total power difference is 1,500 watts, and only 150 watts comes from the chips running more efficiently, what on earth is devouring the other 1,550 watts?
It is entirely consumed by the physical mechanical effort of spinning the embedded cooling fans inside the air-cooled server chassis.
Wait, are you serious?
Yes. At maximum thermal load, those fan modules are drawing upwards of 1,000 watts of power per node.
You're telling me we waste 1,000 watts per server just to spin plastic blades?
Yeah.
That sounds like a catastrophic design failure. I mean, a microwave oven runs at 1,000 watts.
It does.
We are essentially powering a microwave inside every single server nonstop just to create wind.
It sounds insane, but it is a fundamental physics limitation governed by the fan laws of fluid dynamics.
The fan laws.
Yeah. The power required to drive a fan actually increases with the cube of its rotational speed.
The cube.
Yes. So to get just a 20% increase in airflow to combat a heat spike, you need nearly double the electrical power to the fan motor.
Oh, wow. So it scales terribly.
It scales horribly. As the H100s reach 95% utilization, the fans have to hit maximum RPM to force enough ambient air through those dense metallic heat sinks.
And they just become an incredible parasitic drain.
Exactly, devouring a full kilowatt of electricity just to manage the local environment.
If I am managing a facility's power budget, and every single server in my racks is burning a kilowatt of power just to run internal fans, I'd want that accounted for.
Oh, absolutely.
I'd want to see that massive inefficiency on my dashboard. But the paper points out that the entire data center industry has essentially been hiding this waste in plain sight.
They have. And we really need to talk about the metric solution.
Yes, let's talk about that. Because this is perhaps the most disruptive structural revelation in the whole white paper.
I agree. It challenges the foundational accounting metric that the tech industry has used for over a decade to claim environmental efficiency.
The metric they use is called PUE, right?
Yes, power usage effectiveness.
Let's look at how PUE is actually calculated, and more importantly, how it's being manipulated by the architecture of air cooling.
So PUE was designed to be a straightforward ratio. You take the total electrical power entering the data center facility.
And this includes everything, right? The lights, the security systems, the massive external chiller plants, the water pumps.
Everything. You take that total facility power and you divide it by the IT equipment power.
Okay, and what exactly counts as IT equipment power?
Well, the IT power is supposed to represent the electricity used strictly for productive computation, like the servers and the network switches.
So it's basically total power divided by productive power.
Exactly. So a PUE of 2.0 means for every watt of computing, You spend another watt on overhead.
Okay.
And the ultimate theoretically impossible goal is a PUE of 1.0, meaning zero overhead.
Right. And the industry loves to parade their low PUE scores around on sustainability reports to prove how green their computing is.
Oh, they do. But the white paper exposes a massive loophole in the denominator of that equation.
The denominator being the IT equipment power.
Exactly. The loophole stems from a legacy definition of where the facility ends and the IT equipment begins.
Okay, I think I see where this is going.
In a traditional air-cooled architecture, those embedded high RPM cooling fans are physically bolted inside the server chassis.
Right, they're literally inside the box.
And because they are inside the box, the power meter reads them at the node level.
Which means the facility management software categorizes the power going to those fans as IT equipment power.
Yes.
Oh my gosh.
The 1,000 watts being burned just to violently spin plastic blades is categorized as productive computational work.
That is so misleading.
It inflates the denominator of the PUE equation, artificially driving the PUE ratio down and making the facility look far more efficient than it actually is.
It's an accounting trick.
It is.
Right.
Now, historically, when server fans only drew maybe 10 or 20 watts, this accounting quirk didn't matter much.
Right, it was just a rounding error.
But when fans are consuming a full kilowatt per node in an AI cluster, it completely distorts the reality of infrastructure efficiency.
It's like a massive logistics company hiding millions of dollars in fuel costs under their employee payroll budget.
That is a perfect analogy.
Right, because on paper, their logistics division looks incredibly lean and efficient, but the reality is they are just paying the fuel bills out of a different bucket and pretending the trucks run on magic.
Exactly. The air-cooled facilities are getting sustainability credit for computational power that is literally just hot wind.
It creates a super dangerous metric illusion, especially for grid operators who are trying to forecast actual compute capacity.
Yes. Liquid cooling, however, forces absolute transparency.
Because it moves the cooling out of the box.
Exactly. By physically removing those massive embedded fans from the server chassis, liquid cooling extracts the thermal management workload from the node level entirely.
Because the heat is transferred via the liquid to an external heat exchanger or maybe a cooling tower on the roof?
Correct. And those external systems are correctly categorized on the facility side of the power meter.
So they are finally accounted for in the numerator, the overhead.
Exactly. With liquid cooling, the IT power metric finally represents actual, honest computation.
That is huge. And the researchers actually modeled out the mathematical reality of this correction, right?
They did. They looked at a theoretical air-cooled data center with a nameplate PUE of 1.25.
And in the industry, 1.25 is considered highly efficient.
Very efficient. But when they mathematically stripped out that embedded fan power from the IT load and correctly recategorized it as cooling overhead, the illusion vanished.
What did the true PUE jump to?
The true corrected PUE of that air-cooled facility jumped to 1.43.
Wow. A jump from 1.25 to 1.43 is massive.
At the megawatt scale, that discrepancy represents an enormous amount of phantom power that grid planners and financial modelers have just been completely blind to.
And when you scale that phantom power up to a modern AI training cluster, it turns into millions of real-world dollars.
Tens of millions, easily.
So if we take these per-node power reductions and this corrected PUE reality, and we actually apply them to a massive facility trying to train the next generation of AI, what happens to the economics?
Well, the white paper built two highly detailed facility scenarios to quantify this exact economic impact.
Okay, let's go through them.
They wanted to provide both a cautious baseline and a realistic hyperscale projection.
Let's examine the cautious baseline first. They call this the conservative scenario.
Right, so they modeled the facility containing 2,000 servers.
Okay, 2,000 servers. And with 8 H100 GPUs per server, we are looking at a 16,000 GPU deployment.
Correct. They also factored in realistic operational variables, like a 99% uptime and a 10% switching loss.
Real quick, what is a switching loss?
The switching loss just accounts for the inevitable inefficiency of converting AC power from the grid into the DC power required by the server components. You always lose a little bit in translation.
Okay, got it.
But the most conservative assumption in this entire model was their workload distribution.
How so?
They assumed the facility would only run high-intensity, maximum utilization workloads like foundation model, pre-training, about 35% of the time.
Only 35%.
Right. They modeled 50% of the time at a moderate workload and 15% at a low-intensity workload, where the air-cooled fans wouldn't even hit their peak RPM.
So they are really playing it safe here.
Very safe. And just to be entirely fair, they gave both the air-cooled and liquid-cooled facilities the same nameplate, 1.25 PUE, ignoring the accounting illusion for this first model.
Oh, wow. Okay, so even with the stacked deck, what were the results?
They calculated the energy consumption based on a standard commercial electricity rate of 10 cents per kilowatt hour.
Okay.
Under those incredibly safe conservative parameters, the air-cooled facility consumes 150.2 gigawatt hours of electricity annually.
150.2 gigawatt hours, and that translates to what, in dollars?
Roughly a yearly power bill of $15 million.
Just for electricity.
Just for electricity. Now, the liquid-cooled facility, doing the exact same computational work under the exact same safe assumptions, consumes 127.5 gigawatt hours.
Which costs $12.75 million.
Right.
So even if you assume the systems are frequently running moderate or low-intensity tasks, direct-to-chip liquid cooling trims 15% off the facility's total energy consumption.
Yes. You are pocketing $2.25 million in annual savings on a 2,000-node cluster.
Every single year.
Every single year. That $2.25 million alone provides a really compelling return on investment for the initial plumbing and infrastructure required for liquid cooling.
Oh, totally. It pays for itself.
But realistically, that conservative workload model is archaic.
Right. Nobody spends $500 million procuring 16,000 H100 GPUs to let them run low-intensity workloads.
Yeah, exactly.
You don't buy a Formula One car to drive to the grocery store.
No, you race it.
The hyperscalers, the Googles, the Metas, the OpenAI partners, they are running these clusters constantly.
Nonstop. Which brings us to the paper's second model, the aggressive scenario.
But looking at the parameters they set, this isn't even aggressive at all. It's just the reality of hyperscale AI.
Exactly. It's just how the real world works now. The researchers scaled the facility size up to 5,000 servers.
So that represents a 40,000 GPU deployment.
Right. And they fundamentally inverted the workload assumption to match that reality. They modeled 70% of the operational year running at high-intensity, maximum utilization.
That makes much more sense.
And the medium and low tasks were dropped to just 15% each.
Okay. Did they fix the PUE illusion in this model?
They did. They stopped pretending the PUE was identical. They assigned the liquid-cooled facility a PUE of 1.2, reflecting the efficiency of external heat exchange. And they assigned the air-cooled facility a PUE of 1.3.
Which is much more accurate.
Yes. And finally, they adjusted the electricity costs to reflect industrial rates in high-tech corridors like Washington State or California, pegging it at 13 cents per kilowatt hour.
Okay, so what happens when you turn all those dials to reflect the brutal reality of a massive AI arms race?
The math becomes undeniable. In this hyperscale scenario, the liquid-cooled data center consumes 91 gigawatt hours less energy annually compared to the air-cooled equivalent.
Let me stop you right there, because 91 gigawatt hours is a number that is almost impossible to contextualize.
It's massive.
It is. A single gigawatt hour is 1 billion watt hours. So 91 gigawatt hours is the equivalent of powering roughly 10,000 homes for an entire year.
It is literally the electrical grid of a small town.
Yes. And in the air-cooled scenario, that entire town's worth of electricity isn't going toward, training AI or curing diseases or discovering new materials.
No, it is being completely irreversibly wasted on aggressively blowing hot air around a server aisle.
It's just mind-boggling waste. So when you look at the financial conversion of that waste, what is the dollar amount?
The liquid-cooled facility yields operational cost savings of $11.8 million per year.
Almost $12 million.
Year after year for the entire lifespan of the hardware.
Wow.
The environmental and economic imperatives have completely aligned here.
So if a paper co-authored by NVIDIA and Supermicro is publishing these numbers, making it mathematically explicit that air cooling wastes small city levels of electricity and artificially throttles GPU throughput by 17%.
Yeah.
Does this mean we have reached the end of the line? Is traditional air cooling effectively dead for high-performance AI infrastructure?
From an engineering and strategic perspective, absolutely.
It's over.
Air cooling simply lacks the thermal capacity to support the physics of dense, next-generation silicon.
It just can't keep up.
Relying on fans for AI clusters is rapidly transitioning from being an inefficient choice to an impossible one. Direct-to-chip liquid cooling is now a foundational prerequisite for building and scale.
It is such a remarkable shift. I mean, we've gone from examining the microscopic voltage gates on a single chip, fighting for fractions of a degree of thermal headroom,
All right.
all the way out to exposing phantom accounting metrics and tracking the gigawatt scale impact on our public power grids.
The ultimate takeaway is that heat is no longer just a byproduct that facility engineers deal with after the fact. Thermal management is now the primary, active design variable dictating the boundaries of artificial intelligence.
Direct-to-chip liquid cooling gives these massive systems the thermal headroom to operate 17% faster.
It eliminates the parasitic 1 kilowatt drain of embedded cooling fans.
It exposes the PUE illusion, forcing honest infrastructure accounting.
And it saves up to nearly $12 million a year at the hyperscale level.
So if you are tracking the future of technology, understanding the plumbing of these data centers isn't just trivia anymore.
No, it's essential.
As AI integrates deeper into our medical research, our financial systems, and our daily lives, the physical sustainability of this infrastructure actually dictates the limits of our progress.
It really does. The cloud isn't floating in the sky.
No, it is sitting in a warehouse, generating staggering amounts of heat and demanding to be cooled.
It forces us to confront the physical footprint of digital expansion.
Which leaves me with a pretty profound question about where this physical footprint goes next.
Okay, what are you thinking?
Well, this entire white paper proves that removing heat from the flat, two-dimensional surface of a silicon die is the most critical factor in performance.
Right. Getting the heat off the flat surface.
We currently take standard flat chips and bolt liquid microchannels onto them.
Yes.
But if fluid dynamics are now the absolute dictator of computational speed, why are we still conforming the liquid to the chip?
Oh, I see where you're going.
Why not conform the chip to the liquid?
That is a wild thought.
Imagine a near future where AI processors aren't stamped out as flat wafers anymore. Imagine silicon physically sculpted in 3 dimensions, grown organically around microscopic integrated liquid cooling channels.
Wow.
What happens when we stop trying to cool the computer and the cooling system itself becomes the structural architecture of the computer?
It is a fascinating inversion. We would basically be designing silicon based on the principles of vascular biology rather than traditional photolithography.
Exactly. It is proof that no matter how sophisticated our algorithms become, we are still entirely bound by the relentless laws of thermodynamics.
You can train the smartest runner in the world.
But until you take off that winter parka, you'll never see how fast they can truly go.